Today we will start a new topic this is called the pumping lemma. Okay, so far we have seen several ways to prove that a language is regular. There are several ways. For example, you can build a DFA for it. You can build an NFA for it, or an epsilon NFA. You can write a regular expression for it. In fact, later we will see you can also write what is called a linear grammar for the language. All these things establish that certain languages are regular. Okay. Whatever it is, a regular language has a finite description. So there are only countably many regular languages, and there are uncountably many languages. So the immediate implication is this: there must be languages that are not regular. Okay. So question is how to prove certain languages to be not regular. Of course, any construction like DFA, NFA, regular expression, or linear grammar fails. But how do I formally establish that no such construction is possible? Okay. So this is going to be a little bit more difficult than providing a construction. Fortunately, we have a tool called the pumping lemma at our disposal, and we will use it to prove that certain languages are not regular. So this pumping lemma, maybe I abbreviate as PL, used to prove non-regularity. It is never used to prove regularity. Okay, because I will see that this is actually a one-way statement, not an if and only if statement. Certain non-regular languages also satisfy the pumping lemma. Anyway, so the pumping lemma essentially is based upon the pigeonhole principle. It's proof, to be more precise. And it essentially leads to a proof by contradiction. In other words, we will assume that there exists a DFA for certain non-regular language, and using the pumping lemma, for that matter, the existence of that DFA leads to a contradiction. This is the basic idea of any pumping lemma proof. So, in order to see, so we will essentially assume that a DFA exists. This would eventually lead to a contradiction. And in the process, we will use the Pigeonhole principle. Okay, so this is the basic idea of using pumping lemma. So before telling you the formal statement of the pumping lemma, I would like to give you an example. We start with an example. So this is a canonical and classical example. Consider this language. L set of all strings of the form a power n, b power n for some non-negative integer n. So this is a language over the alphabet a comma b. Okay. So I assume that D is a DFA whose language is L. This would eventually lead to the contradiction, the desired contradiction. But then, intuitively, why this language cannot be regular? The idea is that we may have a string like epsilon, which is like a power 0, b power 0, ab. We may have a, b, b, a, b, 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 and so on. A very large number of a's followed by a very large number of b's, the same number. If this is n, this must also be n. Okay. So now we know that a DFA does not have any external memory. Okay. So the only thing that a machine, a DFA, can remember is by using its states. Okay. So the DFA in particular has finite states, finitely many states, and this essentially implies that a DFA, each DFA has a finite amount of memory. In particular, if there are k states, then using these states, the DFA can remember something like log of k to the base 2, this many bits of memory at most. But if we look at this language, L, this n can be arbitrarily large. Okay. So n can be arbitrarily large. And eventually it will become larger than whatever is necessary to store using this log 2 of k bits. Okay. So if n is in particular much larger than this, okay, or maybe n can be very large, in fact arbitrarily large. So the idea is this: all these n cannot be remembered. Of course, here I assume that this remembering of n is necessary, because if you remember n, then when the sequence of b's comes, then you have to validate the number of b's, or the count of b's is same as the count of a's. Okay. So intuitively, this is the reason why such a DFA cannot accept this language and only this language. Okay. You cannot have a DFA D with language equal to L. Okay. But this is only an intuitive proof. Okay. So what is a formal proof? So this goes like this. Okay. So maybe I start with a little bit complicated thing, then I will simplify this. Okay. So once again, this statement is valid. Assume that there exists a DFA D whose language is this L. Okay. So there exists a DFA D whose language is equal to L. Okay, and I assume that let K be the number of states of D. It's a finite quantity. Okay, so a finite, and I may say positive integer. Okay, so now I take a string of this form. Okay, so let's take n equal to ceiling of k by 2. Okay, so then I have this string. Let us call it a power n, b power n, a power k by 2 ceiling, b power k by 2 ceiling. By definition, this is in L, and therefore D must accept this string. Let us give it a name, maybe alpha, because other things like W, U, V, X, Y, Z we will use for some other purpose. For the moment, let us call it alpha. Okay, so since this is in L, D must accept L. Okay, and the total number of symbols in alpha is k by 2 ceiling plus k by 2 ceiling, which is definitely greater than or equal to k. Okay, in fact we would have taken this as ceiling, this as floor. Anyway, it doesn't matter. No, we cannot take this because numbers must match. Anyway, whatever it is, so D must accept L because this is of the form a power n, b power n. Okay, so now let us see what contradiction arises in this process. Okay, so now let us see the evolution of the machine as it reads this string a power n, b power n. Let's say it starts with a start state. Okay, and let us for the moment give it the name P0. Then it reads the first A. It will go to a state called, let's say, P1. Again, it will read A. It will go to state P. And this thing keeps on happening. Eventually, it will go to a state Pn after reading the last A. Then it will keep on reading the B's, Pn plus 1, B, Pn plus 2, and so on. Eventually, it reads the last B and reaches a state Pk, which we may call R or F, whatever, it doesn't matter, which is a final state. Okay. So let us see how many states are here. Okay. There are k symbols. The first one lets it move from P0 to P1. Second one lets it move from P1 to P2 and so on. Eventually, the kth one, kth one will let it move from Pk minus 1 to Pk. So I have a sequence of k plus 1 states. P0, P1, P2 up to Pk. And by the choice, K is the number of states. Well, maybe I made a small mistake. It doesn't matter anyway. This is actually, it is not exactly k, because this is true if k is even, so some 2n. Okay, so they are actually I would state set, 2n plus 1 states. Okay. And so this is, instead of k, let me write 2n. Okay. And k is the number of states of the DFA D. Okay. And we have chosen n equal to k by 2, ceiling. So this is greater than equal to k by 2. So 2n is greater than equal to k. So this 2n plus 1 is greater than equal to k plus 1, which is greater than k. So by the pigeonhole principle, since k is the total number of states and I have something at least k plus 1 states, p0, p1, p2 up to p2n. Okay. So some state must repeat. Okay. In other words, we must have some pi equal to pj. We must have for some I and j in the range 0 less than equal to I, and let's say j is bigger than I. This is less than equal to 2n. Okay, we must have something like this by the pigeonhole principle. Okay. So now let us see what it really implies. So, I have a situation like this, S, then I have pi, then I read some more symbols, and I get pi. Eventually, I end up in R. Let us say the amount of input consumed from S to pi is U. From pi to pj, V. And from this final state, W. So my input alpha, which is a power n, b power n, can be decomposed as u, v, w. U is the portion of the string that the machine reads for moving from the start state S to some state pi. Okay. And v is the intermediate part which the machine reads to go from state pi to pj. And it turns out that pj is equal to pi. Finally, at the end, the machine reads the third part of the input string, w, in order to reach from the state pi equal to pj, the same state, to the accepting state, r. Okay. So what do I have in this case? I have, if delta is the transition function, delta hat starting from S, the machine reads U, it goes to pi. Then delta hat goes from pi, reads that intermediate part V, middle part V, goes to state pj, which happens to be same as pi. Eventually delta hat pi, it reads W, reaches R. Okay. So if that is the case, what I see, if the input is something like this, alpha prime, which is just U, W, just V is missing. And what is delta hat of S, UW? By definition, this is same as delta hat of SU W. But what is delta hat of SU? This is PI. So delta hat of PI W, which is this one R. So this is once again in the final state. So D also accepts this string alpha prime, which is UW, the V missing. Okay. Now, if I consider this, another thing, alpha double prime, U, V, V, W. Okay. U, V square W. Okay. Now, if I look at the working of the machine on this string alpha double prime, so it is U, V square W. Sorry, starting from S, what it is going to do, first it goes to S U, what remains is V square W, and this is delta hat of SU, this is PI, V square W, then this is same as delta hat of PIV, then it will read VW. This is nothing but delta hat of PI plus V, PI comma V is nothing but PI itself, VW. This is same as delta hat of PIV, finally it reads W, which is same as delta hat of PIV is PI itself, then W. By the last equation, this is R. So once again, this is the final step. So D also accepts alpha double prime, which is U, V square W. So now let us see which contradiction these observations may lead to. Consider this string UV. Okay, so once again let us say alpha is A power n, B power n, and this is broken down as U, V, W, and because I is strictly smaller than J, we must have V greater than 0. So V is a non-empty string. This part. Okay, non-empty substring. Okay, so we have also seen that UW. Okay, so this is again in L because the DFA accepts it. Okay, so there are three possibilities. So I have the block of A's, A, B, B. So my V may be inside the block of A. So this is case 1. V may be entirely inside the block of B. This is my case 2. Another possibility is V spans on both sides of the boundary between the A block and the B block. So this is case 3. Which one happens is not exactly in our control, right? So if case 3 occurs, okay, we may have V of the form some A power L, B power L. But then what is alpha prime, which is UW? So you are just removing LA's and LB's. So it will be A power N minus L, B power N minus L. We know that this is already in L, okay? Because count of A's and count of B's are the same. So no contradiction. However, if we are in case 1, number of A's in alpha prime less than number of B's in alpha prime, because you are removing some A's from the block of A's without affecting the block of B's, and still you claim that this alpha prime is in L, whereas certainly it is not in L. So this is a contradiction. Also, if case 2 occurs, you are taking out some of the B's, okay, without affecting the block of A's. So the count of A will now be bigger than the count of B, okay, which implies that this alpha prime is not in L. This is again a contradiction, since the machine is going to accept it, and therefore alpha prime must be in L. Okay, so we could arrive at a contradiction in case 1 and case 2, but if case 3 occurs, if we are unfortunate that we face the situation of case 3, then we cannot arrive at any contradiction. That's not a good thing. Okay, so the proof fails essentially. Okay. Okay. So now let us look at this alpha double prime. U V square W. Okay. Now once again you consider the 3 cases. The block of A's, then you have the block of B's. Case 1, V is completely here. Case 2, V is completely here. So case 1. And case 3, this is my V, case 3. In case 1, number of, I have pumped in some extra A's in alpha. So number of A's in alpha double prime will be bigger than the number of B's in alpha double prime. Still the machine accepts it, so this is a contradiction. Similarly, if we are in case 2, we are actually injecting a few extra B's without affecting the A's. So the number of A's in alpha double prime will be now strictly smaller than the number of B's in alpha double prime. Still the machine accepts it, so this is a contradiction. If we are in case 3, just imagine what happens. You are pushing something like this. So you have this U here. Then you have this A, some A's followed by equal or some number of B's. Okay, sorry, this is U, this is V. So we have another instance of V. Eventually you have W, which is B, B, B. So this is W. Now you see that this string contains a forbidden pattern, BA. Okay. So in case 3, alpha double prime contains the pattern, the substring, BA. So then alpha double prime is clearly not in L because no string in L contains the pattern BA, whereas my alpha double prime contains. The machine still accepts it. So in all the three possible cases, we can arrive at contradictions. So you see that if I worked with this, where do I go? I see. Yeah. So if I worked with alpha double prime, we could arrive at a contradiction if we are in cases 1 or if we are in case 1 or in case 2. That if we are in case 3, we may have no contradiction. However, if you work with alpha double prime, then in all the cases we can arrive at contradictions. Okay. So these contradictions essentially prove that no such D can exist. Okay, which implies in turn that L is not regular. Okay. So this proof is unnecessarily a bit too complicated. So I give you a simplified proof. So instead of taking a power k by 2 ceiling, b power k by 2 ceiling, why don't we take just a power k b power k? Okay. Now the length of alpha is 2k, which is definitely greater than or equal to k plus 1. Okay. And then I can apply the pigeonhole principles, but now what we have achieved is this: A, B, 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 B. So here I am starting at the start state S. This is if it is P0. After reading K symbols from the input, I reach at a state Pk. So now if I count the number of states, P0 here, P1 here, P2 here, P3 here, eventually Pk here. So this gives me k plus 1 states. So a repetition must have occurred in the block of A's itself. Okay. So once again, this decomposition, as we have done in the earlier proof, we can have alpha equal to U, V, W. The only thing is that the length of U to W less than or equal to K, and this essentially implies this is less than or equal to K, but this is at least 1 greater than 0. Okay. Now if I consider alpha prime UW, then you are taking out a few A's, okay, and there is a count mismatch between the A's and the B's. And if I consider alpha double prime U V square W, so you are injecting some extra A's. So once again there is a count mismatch between A's and B's. Okay. So now both lead to contradictions. I do not have to consider any complicated things like case 1, case 2, case 3. Okay. So if I choose my alpha more appropriately, the proof becomes much simpler. In particular, you can see that I can pump. So this is a case which is called pump out B. This is a case which is called pump in V in the input string alpha. Okay. In fact, you can see that for any I greater than equal to 0, if I call this alpha I, this is in L. Okay. The machine is going to accept it. Okay. And this is true for all I greater than equal to 0. So I equal to 0, this is this case. I equal to 2, it is this alpha double prime case. I equal to 1, then this is nothing but UVW, which is alpha. Alpha 1 is alpha. Okay. In particular, you can pump this V as many times as you want. You can pump out only once because there is only one occurrence of V, but you can pump in as many times as you want. And still, the machine is going to accept that string alpha I for all I greater than equal to 0. So for some I, you are going to arrive at a contradiction. Okay. In this case, any value of I not equal to 1 will give a contradiction because the initial choice of this alpha is better than the earlier choice, which is this. Okay, so there is actually no problem with that earlier proof, but this proof is much more simplified. Okay. Okay, so let us look at a second example. Maybe I take something like this. Now my language is L. You may call it L2, a to the power n square, n greater than equal to 0. So what does it mean? The empty string a, 2 square is 4a's, 9a's, then 16a's, and so on. Okay. So this language is not regular. I want to show. So assume that L is regular. Okay. And if so, there exists a DFAD whose language is L. And let K be the number of states of D. Okay. Okay. So now we consider this. This string a k square. Okay. Number of states, so this is in n greater than equal to 1. It doesn't matter, a k square. So this is definitely in L. So D accepts it. Okay. And we also have the length of alpha equal to k square, which is definitely greater than equal to k. And if we look at the working of the machine, it starts at state P0, reaches the first A, goes to P1, this is second A, it goes to P2, finally it reaches the last A, goes to state k square. So number of states is k square plus 1 because I'm counting from 0. This is greater than equal to k plus 1, which is greater than k. So once again, by the pigeonhole principle, there exists I and j, I less than j, such that the state pi and pj are the same. Okay, so it is repeated. So once again, something like this, I, j, finally. So this is my entire alpha. Start at R, reach at, this is start state S, reach at some final state R, some pi, some pj is repeated. And here I have I'm running out of expression, maybe A. Okay, some number of A's are here, A. Then some number of A's are here. Finally, some number of A's are here. Okay. So this part is non-empty because I is less than J. Okay. But this state is same as this state, so it doesn't matter. If I pump out this, the machine is still going to accept this. If I pump in this, the machine is still going to accept this because Pi is equal to Pj. The proof is exactly the same as in the earlier case. So in particular, if the length of this part, so this part let us call U, V, W. Okay. So U is a power something, V is, let's say V is a power L, where L is greater than or equal to 1. Okay. So once again, because pumping out once, pump out 1, you will be left with minus L. Okay. But if you pump in, you can have any IL. Okay. So let us call this string alpha I. Any such I is accepted by D for all I greater than or equal to 0. Sorry, again a mistake. This should be, okay, actually N is nothing but K square that we have taken, K square, and IL, a power L you are pumping in or out. Okay. So in particular, if I is 1, K square minus L plus L, which is same as K square. Okay. This is the original string. Otherwise, if I now look at alpha 2, A K square minus L, A 2L, K square plus L. This is accepted by D. But note that this length L that is pumped, this is bigger than 0, but no bigger than K. So K square plus L is less than or equal to K square plus A, K, which is strictly smaller than the next square, which is K plus 1 whole square. Okay. So since D is a machine for the given language L, it should not accept the string whose length is K square plus K, which is not of the form K plus 1, K some K square. Okay. So D accepts alpha 2, which is not of the form a power n square. So this is once again a contradiction, indicating that no such D can exist, which in turn implies that L is not regular. Okay. So this is how the existence of a DFA can lead us to contradictions. So now I formally state the pumping lemma. Of course, this is for regular languages. We will later see a pumping lemma for context-free languages. Okay, it goes like this. Let L be a regular language. Then there exists a positive constant integer K such that for any string alpha in L with the restriction that length of alpha is greater than or equal to k. Okay. For any string alpha in L in this language with the length of alpha greater than or equal to k, we have the decomposition alpha equal to u v w. Okay. Okay. I will make it a little bit. Okay. Let me do this thing. Instead of doing this, for any string, for some convenience, I will just not consider alpha as such. I will do something. I may have something like this: x, y, z in L with, so this is my alpha, okay, with the middle part y greater than or equal to k in length. We have the decomposition y equal to this, such that, or we have a decomposition, there are too many such debts, so let me write it this way. There is a decomposition of this form, the middle part y, whose length is greater than or equal to k, satisfying the following three conditions. One, this middle part v is non-empty. Okay. So this is non-empty, and this is the part that we are going to pump in or pump out. Second, this pumping in happens not too far away from the beginning, so this is less than or equal to k. And three, x is first read, then y, u, v power I, w. Finally, z is to be read. This is in L for all I greater than or equal to 0. Okay. So I'm not going to form a proof of this. So this v part you can pump in or pump out. You can pump out only once, and you can pump in as many times as you want. So V can be pumped out once or pumped in as many times as you want. Okay. So this pumping lemma is a property of regular languages, but not an exclusive property of regular languages, because non-regular languages, some non-regular languages also satisfy the pumping lemma. But if we want to prove certain languages are not regular, this pumping lemma is helpful because you assume that it is regular. Okay. Then there exists a constant k. So this is called the pumping lemma constant. We know that this is the number of states in a DFA for that language. Okay, but we do not have to talk about the DFA and all that stuff. This k is just a positive constant integer. As that, if you take any string of the form xyz, okay, with the middle part sufficiently long, then you have a decomposition and all these three properties. Okay, so proof, formal proof of this, I leave it to you. It's exactly the same as in the previous two examples. Now, eventually, let us see how this can be used this lemma can be used to prove certain language to be not regular. Okay, so U, then you have daemon. Okay, so you get a language L, which you want to prove to be not regular. Okay, so you assume that this is regular. Then the daemon gives you the pumping lemma constant k. You have no choice over k. Okay, so this is k is picked by the daemon. Okay, and gives k to you. Now you are free to choose your initial alpha of the form x, y, z. This is your choice. Daemon cannot control it, and you supply this to the daemon. Daemon in turn gives you the decomposition of u, y in the form u, v, w, and gives that decomposition to you. Okay, so you have no control over k. You have no control over the exact decomposition of y into u, v, and w. This is done by the daemon. Okay, now you choose x, y power I, u, v, w, it's there. Okay. So you now choose I in x, u, v power I, w, z. Okay, this is your choice. So make it very clear that you have no control over k. Or the decomposition of y. It's a daemon's job to give you a value of k and a decomposition of this form. What you have full control is alpha and the I. Okay, so you have full control over your choice of alpha and I. So this machine, okay, so by the pumping lemma, this will be in L, and from a description of L, your choice of alpha and I will eventually lead to the case when this is certainly not in L, and that will lead you to a contradiction. Okay, so this is how we are going to use the pumping lemma to prove the non-regularity of certain languages. Okay, so once again I highlight k is a positive constant. Apart from that, you do not assume anything about k. Here there is a decomposition. Apart from that, this v is non-empty, and the length of uv is less than or equal to this constant k. You cannot assume anything. So you have to carefully choose alpha and I such that you can eventually arrive at a contradiction. Okay. So your choice is alpha and I. The demon's choice is K and this decomposition UVW. Okay. Okay. So just to be a little bit more concrete, so let us look at this example 1, where I have taken x equal to z equal to empty, whereas I have taken y to be the full thing, a to the power k by 2, b to the power k by 2. Okay. And in the second proof of the same example, a power n, b power n, we have taken x equal to empty, y equal to a power n, z equal to b power n. That simplified the proof. And in example 3, a power k square, a power n square, we took x equal to epsilon, y equal to the entire a power k square, z equal to epsilon. Okay. So we will let us see that by different choices, these choices of x and z gives us a little bit more flexibility. Okay. Instead of just taking y. Okay. Okay. So I think I stop this lecture at this point. So we will see more applications of the pumping lemma in the second lecture on it. So see you. Bye.